Good morning, folks. This is Todd Coburn of Cal Poly Pomona with your Aerospace Structure series. This lecture is going to be the start of a two-part series on basic fracture mechanics analysis. We're going to learn some of the basics, the foundational concepts today, and then we'll continue that in the next lecture to look at how we can grow our cracks and estimate the life of a part using this kind of approach. Okay, so let's see how it works. Now, we've seen in the last few lectures how to evaluate the life of a part that is under cyclic loading using a fatigue approach. That approach used data, test data, of a part subjected to fully reversed stress, and we came up with a set of curves that express how the fatigue strength or stress level relates to the number of cycles to failure. Now, fracture mechanics or damage tolerance uses a completely different approach. And what we do in a damage tolerance kind of analysis is we either measure whether there are cracks in the part or defects, or we assume a crack level. We base that usually on how on our inspection method, what's the smallest crack that we can see, and then we assume a crack of that size and then evaluate how that crack propagates through the part. When we're using a fracture mechanics approach, we're going to look at three different basic types of crack growth. Mode 1 is what we call an opening crack. If you have an edge crack in a part, as you see in figure A here, and under tension load, if that crack opens, actually we call that an opening crack. If shear, mode 2 is when we're shearing a sliding crack, where we have a shear stress that slides the part along itself along that crack. Crack is like this and we see it sliding. And a mode 3 is called a tearing mode, and that's when we're ripping it like this. Now, fracture mechanics is done for all these kinds of modes, but the most common one, the one that's generally most critical and the one that's focused on mostly in aerospace, is this opening crack that we're calling a mode 1 crack. Okay, so that is going to be the foundation or the focus of our study here in this little introduction to fracture mechanics. So the foundation for this approach that we're going to use was laid by Griffin in 1921. And basically what he did was he assumed an elliptic crack and a semi-infinite plate. And he called the dimensions, now this is not the whole dimension of the ellipse, this is the half dimension. So A is half the width and B is half the height of the thing, right? And he said, well, the stress is actually roughly whatever the Farfield stress is. We're back to this Farfield word. When we use this word Farfield stress, what we really mean is, hey, we've got a semi-continuous structure, and what's the stress level if there was no problem, no cutout, right? Normally what we're doing is taking, like, let's say we have a part loaded with a force, we've got P over A as our gross stress. We could call it the gross stress, the average stress, and if there's no little cut or hole, that's also the net stress. But if there's a hole, then we have a net stress and the gross stress. Now, as this gets larger and larger, let's say like the skin of an aircraft, where it's hard to define like what width of the skin is there because it goes beyond where I'm really focused, then that has the idea of a far field. The far field stress is just the P over the total A, whatever the stress level is uniformly through here. If somebody has a hole right here, we're going to expect a stress concentration, but if we're using the far field stress, it's the stress as if there was no hole. Rather than normally when we're looking at stress concentration, we're going to take the net stress first and then apply the stress concentration factor. Farfield stress has the idea that we're going to calculate the stress level as if there's no free feature, no interruption in the part. Okay, so we're using the Farfield stress, and if you take the Farfield stress sigma, then this little equation here will give you the stress in the y direction, and we can see that that peak is going to happen just to the two edges. If the little ellipse is here, we're going to see it on both edges of that ellipse. this stress here. And it's a function of those A over B ratios. Now, if you think back and you say, okay, let's say we have a round hole, then that means A equals B. If A equals B, then actually your stress is just 3 times. 3 times the Farfield stress. And if you look at what we did before, looking down here at the bottom, stress concentration factor, we found the same thing for a uniaxial load. If you have a centrally applied hole and a rather thick part, then your worst case stress concentration factor is going to be about 3. So this kind of aligns. Now the next thing he did was Griffith postulated that crack growth is going to occur rather than looking at the stress itself when the energy release rate from the applied loading exceeds the rate of change needed for crack growth. Then he went on to postulate, okay, so that's when crack growth happens, but what we're really concerned about is not crack growth because we don't care if we have a crack growing. It's kind of like life, right? All of us are dying. Some of us are dying at different rates. We all are only here for a period of time, but normally that idea of dying doesn't trouble us unless we find out like we're going to be dead next week. If our rate of dying increases in some unstable manner, that's where we get nervous. In the same way, since parts are people too, it's not the crack growing that's so much of a problem, because as long as we can analyze how fast it's growing and we see, hey, well, actually we're going to be done with this part before that finishes breaking the part, so that's acceptable crack growth. What we're worried about is evaluating when does crack growth become unstable? When does it begin to happen so fast that failure is imminent? And so he says that unstable crack growth is going to occur when the rate of change of the energy from the applied loading exceeds the rate of change of the energy, rate of energy required for crack growth. So that is what we're going to use. Now we're actually going to break this down, make it a bit simpler, but that's the general idea behind it. Got it? So going back to his model, now let's switch from that pretty little smooth ellipse that we had and make it a little more jagged diamond-shaped part. Once again, our A is the half width. And if we wanted to calculate the stress at the tip of the crack, we can see that it's a function of our Farfield stress sigma. And we can see, so imagine that here's our little diamond shape. I'll just do it like this. Here's our little diamond shape. Right here, we're going to expect the maximum stress, right? If we had no feature, we'd expect to see the Farfield stress. If we have this cutout that's shaped like that, we're going to expect the maximum to be right there. Now, as we move further and further away from that tip, we're going to expect the stress to drop from this peak value to something closer and closer to the Farfield value. Eventually, you're going to get to the Farfield value because what we're going to see is the Farfield stress unless we get close, and then the stress is going to start climbing up. Got that? Now, the other thing you might think is, well, actually, although it's a peak here, what's going to happen is that means all the stress lines that came like this are kind of tightening right through there. That's why it's so high. But out here, they didn't have to change much, so the Farfield stress still applied. But then as you move away, what's going to happen is the loading is going to come back and work its way back through. If you move far enough away, the loading will be uniform again. So not only will the stress change as a function of the width or radius away from here, but it also changes as a function of this dimension here. Now we could put in like an X and a Y coordinate of that, or we could put like an R, how far away from the feature, and a theta. So theta 0 is along this line, theta 90 would be directly above it, and so on. So the way Griffith postulated is here, where this work has been extended, is we're going to put in an R and a theta to locate where we are. And we can see if we take the Farfield stress, we can just use some function of this R and theta to calculate what the stress is at those points. That's what these three equations do. It's going to give us the stress in the X, Y, and the shear stress as a function of what the Farfield stress is, what the radius is, and what that angle is. And this is all developed straight from trig, okay? You got that? Now, we're going to take that a little further then. If we define our stress intensity, so here's a new parameter we're going to define called the stress intensity factor, okay? The stress intensity factor we're going to define, K1, is, now this looks like Ki, and I'm a little sloppy in my terminology because stress intensity, right, starts with I often say K sub I. But actually it's not K sub I. What it is K sub 1. It is the stress intensity, yes, but what the little 1 is drawing our attention to is the fact that this is a mode 1 crack. Remember, we're only going to be doing mode 1 crack, but when you say K1, you're seeing that that's a mode 1 crack or an opening crack. We're defining that mod factor is the Farfield stress sigma times the square root of pi a. Now this is kind of a weird unit, which is going to give us kind of strange units. This means we're going to have units for stress intensity of PSI square root of inches. If that's not a weird unit, I don't know what is, but that's what unit we're going to use. So the Farfield stress times the square root of pi a. Got that? Okay, now you got to be warned here. Some folks use this equation like that for stress intensity. We're going to tweak it in a moment because this doesn't have quite enough information and use a different form than this. But if we start with this and this, we define our stress intensity this way, and then we substitute this equation back into our original 3 equations, then we can rewrite the equations as shown over here to the right, where we now have our stress in the x, y, and the shear stress as a function of our stress intensity. Okay, we're getting closer to what we're going to do. Now, the stress intensity factor is a function of geometry, size, and shape of the crack and type of loading. But if you think about that statement that I just made and you look at this equation, it doesn't look like we have a whole lot of this information. This statement says it's a function of geometry, size, shape of the crack, rope, and type of loading. However, if you look at this equation, all it's a function of is what the Farfield stress is and what that crack length is. Now, here's another place to be warned. We're calling the crack length A, but if you look at our picture, that's not the crack length at all. The crack length is really 2A. But what we're defining is we're defining the crack length parameter as A, which in this case is 1/2 of the crack size or width. So this is another thing you're going to have to be alert for when you're doing damage tolerance. When we talk about what's the crack size, right? If we spot a crack, we're talking about what the actual length of the crack is. But if we say what is the crack length, A, it's a function of what type of crack we have. And often that A is the whole crack length, and often it is actually only half of the crack length. And that depends on how that crack is defined and how it meets our parameters. We're going to find out more about that in a minute, but you need to be alert to that already, okay? So we see that the stress intensity, K sub 1, is the stress level and the square root of pi A, where A is the crack parameter. Often the crack length, but sometimes it's half the crack length. Now we're actually going to find out, because this doesn't tell us enough, all this has is the crack size and the stress level, we're going to introduce another parameter, beta, to introduce more information about the loading, the geometry, and that kind of thing. Let's take a look at how that works on the next slide. For example, let's say that we have a central crack, a through crack in a part. Let's say I have a thin plate, and this plate has a crack in the middle of it. The loading is going axially, but the crack dimension, or the width of the crack, goes perpendicular to that crack. And this crack is located right in the middle. We're actually going to use a slightly modified form of our stress intensity equation. Our K sub 1 is going to be beta. We're going to use beta to be a parameter. We're going to call it the stress intensity modification factor. That beta is going to accommodate the idea that this is a central crack. So we're going to use this other form, K1 equals beta max stress square root of pi A. Now if we have a central crack, as we see here, we have a part of a certain width and a certain thickness with a uniform stress on it, axial stress. We're going to set our crack dimension or our crack parameter is going to actually be 1/2 of the crack length. So A is actually 1/2 of the crack length. You can see that because it's written as 2A here. So we've got a stress level, we've got this crack length 2A, and we're going to calculate beta. We can use it, we can either read it off this curve. So this means if we're reading this curve, we would see for a value of 0.2, A over B ratio of 0.2, it looks like our crack is going to be about a 1.1, or beta is 1.1. If we have a crack A over B ratio of 0.3, that looks like our crack length is, or our beta is 1.3. A crack length A over B ratio of 0.4 says we have a beta of 1.8. And if we have a over B ratio of 0.45, it looks like we are at 2.6 is our beta. So we plug in our beta here, we take our maximum stress, pi, and that crack parameter A, which in this case is 1/2 of the crack actual length, where the crack length goes from there to there, and our A parameter is 1/2 of that value. Now, if we actually are between points, we can use this equation to get a more accurate estimate of our beta, of our stress intensity modification factor. The stress intensity modification factor is introducing some basic loading and geometry information. Now, some folks and some references will take this beta parameter and break it up into 2 parameters and give 2 different ways of calculating the 2 subparameters that give you a total of beta. But for our purposes, this is a general enough approach that is used by enough folks to give us a reasonable foundation. Okay? So, once again, if we want to estimate the stress intensity for our part, we're going to start by figuring out what is the maximum stress on the part, what is the what kind of crack do we have. If it happens to be a centrally located through thickness crack like this one, we will take the total length divided by 2, and that will be our A parameter. We will then look on this, we'll calculate the A over B ratio, where B is the width of the part, and we will calculate our A over B ratio, and then we will estimate our beta. Now let's say that we have, so how many parts look like this thin plate? Well, maybe not a whole lot of aerospace parts look like this. But if we're talking about a skin, a lot of times we can say, well, let's say we have a bunch of fasteners in a part, and we have a Farfield Stress sigma that's a maximum stress of some value. A lot of times we can say, well, we will just take this, we will pretend that our part is this wide, we'll call that B, from the edge of this hole to the edge of this hole with this centrally applied hole. This is 2A, we'll set this to our B value. So if this spacing is S from center to center, it looks like we've got 2S minus D is our total width of this part, and we can use this curve in this manner. On the other hand, let's say we have an angle, and let's say that this angle has a edge crack like this. If that were the case, or excuse me, this is not an edge crack. Let's do a different one. Or for example, if we have, let's say, a hat stringer, and let's say that this is an isometric one, and it goes like this, and somewhere along the thing we see, let me draw it differently. Let's say it looks like this. This will be easier to see. This is the symmetric part, and it's going like this. And let's say there's maybe a bunch of holes, and so we get a crack running right here, and its dimension is 2A. Well, we can actually fold this part out. We can take this dimension from here to the half length. We'll call that B1 plus from half length to half length B2 plus half length to half length B3 plus half length to half length B4 plus half length to the edge B5. Sum up that B1 plus B2 plus B3 plus B3, 4 plus B5. That is the total B of the part that this crack is centrally located. We can figure out what that half crack length parameter is, calculate our A over B ratio, and we're back in business. That's how we can estimate or solve those kinds of problems. Okay, so with that said, let's say we get two edge cracks that are symmetric on the part. If that's the case, once again, now our crack parameter A is going to actually be the crack length. And so we're going to take that A and plug it into our equation. We're going to calculate our A over B ratio. We're going to find it on this curve and read our beta. Now, to get a more accurate level, as you should in this class, we can use this equation here to give a nice precise value of what that is. If we have that same part, that hat stringer we were talking about before, and let's say that that part experiences, we find an edge crack that's located here, and we have another one on the other side that's located over there, we can use this same method. Once again, looking at things, we've got a crack over on this side and a crack on the other side in the same location. We'll take that crack length, we'll calculate that same folded out B value, effective width of the part, and we can plug in those values to get our A over B ratio, which we place here with our max stress and our A parameter to get our stress intensity, K1. Got it? Okay, how about if we have a different part? Let's say we have something that looks like this. We have a single edge crack, for example. Let's say we have a part like this. For example, let's say we have an angle, and let's say this angle we have discovered an edge crack on the angle that's sitting right in there. Okay, that edge crack, we look at this and we say, well, that's our A dimension. Great. And we can say, okay, this angle from here to the half width, we'll call that B1. From half width to the end, we'll call that B2. So the B for this part looks like B is our dimension. B equals B1 plus B2. Notice that's going to the half thickness, not to the edge of the part. That's going to be our B. What's our A? It's right here. So our A over B ratio, we calculate that, we enter this, and we just read the curve for our beta. Or better yet, plug into this equation to calculate the beta. We plug in our beta here, max stress there, our A parameter there, we calculate our K1. That's for an edge crack. Or if we had that hat stringer, but we only had that crack on one of the two edges. Okay? If we have, now you'll notice this looks quite similar. We have an edge crack again, but the loading is different. Now what we have is bending on the part. For example, parts that might be like this would be if we have a, let's say we have a thin part like this with a bending moment that goes like this with a edge crack on the side that's getting tension. Or if we have, let's say, how about a Z stringer? And let's say that this Z stringer has a crack right here, and we see that we're getting bending maybe about this axis, going like this, a bending moment like this. That's going to introduce that kind of bending. It's pulling tension on this side and compression on this side. Now this is not precisely the same because you'll see that stress is 0 all through here. But if you fold that out, from here to here is B1, from here to here is B2, from the middle of the thickness to there is B3. So B is the summation of those little B segments. Take our A dimension, A over B ratio here, and we can read our beta and plug in our values. Got that? That's how that works. Here's another one. This is a little trickier. In this case, we have a hole. Now we have a lot of holes in aerospace, and a lot of times we start the cracks from there. So if we get a condition like this, we're going to look and say, okay, what is our A over B ratio? First, we'll take the distance from edge to edge, and we'll call that 2A. So A is half of that value. Okay. Then we're going to go and calculate our A over B ratio. Great. Then we're going to select the curve, our R over B ratio. So if the radius of the hole is 0, if there's no hole, just a central crack, that should be very similar to our earlier curve, and that would be this curve down here. Now if our hole radius is 1/4 of our B dimension, then that means we've got this curve here, and we would read that curve for our beta. If that is equal to 0.5, then we can read this for our beta. In my handbook, I give you curves or equations for these curves, which you can use to give a more precise number. Otherwise, we will just read the curve for the values, plug in the A, plug in the beta and the alpha. Now, I don't give you a condition like this in the handbook. And there are actually curves for this, but I don't give you one. So if in arrow 3261 we get a hole with a single-sided crack, we will approximate this as being 2A and use this curve. That's not strictly correct, but we can do it for our practice introductory stuff. If you're out there in industry and you get one that's shaped like this, then you're going to want to go and find an appropriate curve or use NASCRO or AFCRO, which has a database of values. Okay? All right. So with that said, we're ready to talk about, now that we understand how to calculate K1 for the part, we're now ready to learn about what is the critical stress intensity. So we've now seen that we can get a pretty good estimate of K1, our stress intensity, for any loading in geometry by finding the correct curve, calculating the beta, figuring out what A parameter is valid with that curve, and calculating our stress intensity K1. Now, if we test materials, we're going to find that many materials, the materials we're going to run into in aerospace, they tend to have a critical value. A critical value. So if your K1 is below that value, then you get a nice stable crack growth. There's actually a value of K1 that's so low that you won't get any measurable crack growth with huge amounts of cycles of loads. But over most loadings, the crack will grow, that means your K1 is going to grow with your K. As your crack grows through the part, your K1 is increasing by the square root of that, right? Not only that, your K1 is your K1 increasing because the A is increasing, but your beta is going to be changing because that A over B ratio is increasing. So you're kind of getting a double effect. You're getting the square root of A that's causing it to increase, plus you're getting beta that it's increasing, and a lot of times that increase is nonlinear. However, we're going to find that it will continue to grow in a reasonable fashion until you reach this critical stress intensity, and then the crack is going to tend to grow quite rapidly and abruptly. So we want to stay away from that critical value. If you look in your handbook, here's some rough approximate values of the critical stress intensity for some common groups of materials. I will probably, with the second edition, put a few more values because actually the critical stress intensity for aluminum and titanium, and actually each of these materials can vary quite a bit based on the different material, the form of the part, whether it's an extrusion or plate, based on the temper of the part and other factors. But we'll use these in this class as a general thing. Also, we're going to find that there's actually some better data for these parameters C and M. Now, we're not going to use the C and M yet. We're going to use it next lecture. But this table has all that information that we're going to use. Okay. So these are some typical values that we're going to use. K1C is a material property that is a function of things like material crack mode and other things. Okay. K1C is our fracture toughness, and we call this the mode 1 plane strain fracture toughness of the material. Okay. Now, so this means once we understand that K1C is a value we don't want to go over, so this is only a tiny piece of the fracture mechanics work we're going to do, but we need to make sure we don't exceed K1C. So the first thing we can do with our fracture mechanics, the most simple thing we can do, is make sure that for any crack size we are not going to fast fracture. We can write a margin of safety against fast fracture by just taking K1C divided by K1 minus 1 in the standard method. If the value is negative, we need to be redesigned, and if it's positive, that means fast fracture doesn't occur. Now, this crack will probably still grow as we get repeated loading, but at least we know we're not going to fast fracture at this point. So this is the main thing we're going to focus on this lecture, is being able to evaluate fast fracture of a part. All right, so if we want to evaluate fast fracture of the part, what we're going to do first is determine the K1C for the material by going to our table, 431 in our handbook. Okay? We then need to determine what our initial crack size is. Either that's given to us in the problem statement, or it's going to be a function of how closely we're looking, or we're going to assume a crack size based on what we can see. Okay? We then are going to calculate the initial beta. Remember, beta is a function of geometry of the material, but also of a stress level. So we're going to go and calculate what our beta is. Okay? We then calculate our maximum stress. Remember the Farfield stress, the value we're going to use is the maximum stress. Now, when we're doing this analysis, we're going to use two parameters here. We're often going to use the max stress. Whenever we go to the stress intensity equation, we're going to be using the max stress for that. Later, we'll find that the change in stress will be valid. We'll be using that later. Don't get confused. Right now, we're focused on the maximum stress. Okay? So we calculate the max stress at the crack tip. And then what we're going to do is calculate our K1 for the part using this equation. This means we're going to have to go and use the initial beta, the max stress, and the crack length at that stress level. You see that? Now once we have this, that's the K1 for that stress level and crack size. Okay? Now we can evaluate fast fracture. Does the part fail at that stress level? If it does, we have to redesign the part. If it doesn't, we can continue to analyze the crack growth. Okay? And we can write our margin of safety for fast fracture. This is how we evaluate fast fracture. Now, once again, if this margin is positive, we're going to go on to calculate how that part responds under repeated loading. However, we're going to look at that next lecture rather than this lecture. Right now, we're going to stop at just evaluating fast fracture and a couple other related items. So we're going to look at a couple ways of figuring out. So we just validated that fast fracture either did or did not happen for the current stress level and the current crack size. True? Okay. Now what we're going to do is figure out, okay, well, if our crack grows, what's the final crack growth at which fast fracture will happen for that stress level? Now remember, with fracture mechanics, we're calculating a stress intensity, but we're not calculating a stress concentration factor. We're using that Farfield stress. So regardless of how that crack grows, we're using the same maximum stress in the part. All we're doing is coming up with new stress intensities based on the shape and size of our crack. So Once we have a maximum stress, we're going to continue to use that maximum stress in our calculations. And since we just found that the fast fracture doesn't occur for a crack of a certain size, but now we're going to say, okay, at what size will the crack actually cause fast fracture? Now to do this, we're going to look at two different approaches. I used to give you guys three approaches. I'm going to break it down to two. This one we're going to call our approximate method, and the next one we're going to call our accurate method, okay? The approximate method we're going to use sometimes whenever I ask you for the approximate method and for other certain kind of times. And the average, the more accurate method, we're going to use at other times. Here's how it works. We're going to calculate our initial crack size like we did on the last slide. We're going to calculate the beta associated with that crack size. We're going to calculate what our max stress is. We already could have done that. And then we're going to calculate what final crack length this K1C, beta, and stress level all predict by plugging into this equation. This predicts an estimate for the final crack size. Now, this is not the final crack size. It would be if beta is correct. But K1C is a material property. That's not changing. Your max stress is the stress on the far field, so that's not changing. But beta is a function of our crack size. So if the crack that we start with is different than the crack that we finish with, it's very possible or even probable that the beta is going to change between those, and this will no longer be an accurate estimate. So we're going to use this to estimate our first estimate of the final crack size. Then we're going to go and recalculate the beta at that value. That's our final beta. Now in this case, this is the approximate method, so we're not going to try and get it perfectly right. What we're going to do is use this final beta associated with that approximate final crack length. We're going to use the initial beta, and what we're going to do is estimate the actual beta as the average of those two in this manner. Once we have that, we then can evaluate fast fracture by taking this. We've got our K1C, we've got our average beta, and our maximum stress level. Okay, so what this means is we calculated the final crack length based on our initial crack size and our initial beta. We then calculate the beta associated with that final crack length. We use the average of those two to come up with a new beta. We do one more step to calculate a final crack size using the average beta. And we're going to assume that that is valid. That sometimes will be accurate enough, other times it will be grossly wrong. You want to put this in your handbook because this is stated a little more clearly than what I have in your handbook. So I'm recommending here you put it on page 412 of your handbook and put a pointer from where the other procedure is in your handbook. Okay? This is what we're calling the approximate final crack length method. Now, if we want a more accurate one, we're going to follow a slightly different approach. We're going to start off the same way. We're going to get our K1C for the material and our maximum stress. We're going to figure out what our initial crack size is, determine a beta for that crack size. We're going to then estimate our final crack length using the same equations we did before. Okay, this is all the same so far. Then what we're going to do is look at that final crack length and find out, is that different than what we started with? If it is different, we may need to iterate. So rather than iterating back and forth by plugging in this value, what we're going to do is, if this is different, we're just going to assume it's a little bigger. So let's say we start out with a crack size of 0.005, and then we calculate it's like 0.2 is the final crack length. Rather than using 0.2 in the equation, what we're going to do is go back to 0.005 and say, okay, let's go to like 0.1, right? Or 0.01. Come up with something slightly bigger, maybe twice the size or a little bit bigger, and calculate it again, and then calculate our final crack length. And we're going to go back and forth until our solution converges. This is a good way to assess what the final crack length is. So this is what we're going to call the more accurate final crack length, and you want to put this in your handbook, okay? And put it on page, in the extra pages for this section, okay? Got that? All right. Two other things we're going to do is estimate critical forces. So sometimes we'll say, hey, what force can this part take without having fast fracture, we can use our same equation where A is the area of the part, K1C is the critical stress intensity, plug into this equation and estimate what the max forces the part can take. Or if we want to know what's the force where we start yielding the material, we can just plug in FTY in this final equation, okay? I'm not sure that this is as clear in your handbook either, so be sure to print this out and paste it into your handbook. I meant to update this at the last update, and I guess I missed it. Okay. Here's a little example. Let's say we have a part like this. This is the material. Here's our allowables, endurance limit, blah, blah, blah. Do we need the endurance for limit if we're doing fracture mechanics? No, that's for fatigue analysis. We're doing fracture mechanics. We don't need that. We do need the K1C, which we see here. This looks like an edge crack, so we can go and find which curve applies. And what we're looking for here is the minimum force that will precipitate uncontrollable crack growth and the min force that will cause material to yield. Okay? We can do that like this, where we first find our curve. We then go and calculate our area. We calculate, remember this is not the net area but the gross area since we're talking about fracture mechanics. We can calculate our little parameters, read the curve to get our beta or plug into our equation. We then can calculate what these two equations apply, and so we can grab our K1C for the material and calculate the force, the critical force at which we're right on the edge of fast fracture, okay? And then if we want to know what the min yield to cause the material to yield, we just plug into our second equation that gives that value. Does that make sense? You see how that works? Okay, let's look at a couple conceptual questions. How do we idealize this part? Looks pretty clear. Looks like 2B is just, or excuse me, B is just H. It looks like B is actually the H dimension, the distance dimension, and L is the total length. I'm going to look at my handbook since this slide is a little unclear. So we've got H, the parameter H is on the side of the curve, so H looks like it's B. Our B is the figure's H, and B is the width of the plate, so our H is that's B. So notice I'm using nomenclature to define the part, but we need to convert that nomenclature to what do we find in the figures that we're using, okay? Our crack length looks like it's A is equal to W. Our force is central. So our stress is just P over A, where A is just H times the thickness, right? How about this guy here if we have this little part? Now there's two ways we can do this. We can do it on a flange-wise basis. If I say calculate this on a flange-wise basis, we can calculate what the stress is in this flange and just pretend this flange is the only thing there is. In that case, the B in the figure will just be this dimension 1.1. Or if this part is in bending, then that's actually a really good approximation. If this part is in tension, though, then all the stress on it is the same, and our B dimension that we need might be 1.1 plus 4.5 plus 1.1 minus the thickness, because actually it's going to be 1.1 minus half the thickness plus 4.5 minus the full thickness plus 1.1 minus the half thickness. So we assume that that whole part is effective and then calculate that width. So this is the way we're going to do this. If we have a little part like this, this is similar to the homework. We can either assume that the flange is effective, which means 0.75 minus 0.03 is our flange width. This is appropriate if we have bending and the max tension is on that flange. Or we can assume that the whole part is effective, in which case we'd take 0.75 minus 0.03 plus 1.125 plus 1.25 minus 0.03 minus 0.03 plus 1.125 plus 0.75 minus 0.03. If we assume that's the total length, plug that in as our B, that would be appropriate for like an axial kind of load. So make sure you practice that, study it out. If you have any questions, log into the Zoom session. Let's talk about it. Enjoy.